So the predicting part in part A is just to describe some of those transformations. The 1/4 is going to cause your amplitude to only be 1/4. That's going to be a vertical compression by a factor of 1/4. The 3 inside is going to be a horizontal compression by a factor of 1/3. It's going to change your period to 2 pi over 3. The pi over 6 is going to move it pi over 6 to the left. And finally, the plus 2 is going to move it up 2. Now, if we're going to graph this, with the DAB-C, start with your D value. That's your sinusoidal axis. It's plus 2, so we're going to label y equals 2 as a starting point. The amplitude is 1/4, so that means you're going to go up 1/4 and label a maximum at 2.25 and down 1/4 and label a minimum at 1.75. So this is a pretty narrow graph as far as when we're finished graphing this. Since our B value is 3, our period is going to be 2 pi over 3. So we just pick a random spot and label that as our period. Then we can divide this into 4 equal sections. Half of 2 pi over 3 is pi over 3. Half of pi over 3 is pi over 6. 1 pi over 6, 2 pi over 6, 3 pi over 6. So we could label this as 3 pi over 6, or if you wanted to simplify it to pi over 2, that would be fine as well. So now that we've labeled D, A, and B, we're going to graph this temporarily. The dotted line, it's a coast graph. Where does coast graph start? Coast graph starts at a maximum. So go maximum, then minimum, back to the middle, down to the minimum, back to the middle, and back to the maximum again. And so we've got, this is our graph. Now finally the C value says plus pi over 6. That's going to move pi over 6 to the left. So on our scale we've already got pi over 6. We know that that distance is this far, so I'm going to mark negative pi over 6 over here so that I can see it. And I'm going to take each of my points and move it that far over. So there we'll have one there, one here, that one will go there, there, and there. And now we can draw a smooth curve through those points and graph it. Now, for the most part, we've graphed it over everything. This question did say to graph from negative 2 pi to 2 pi. Well, I would run out a board right now because I didn't plan for that when I initially drew it. Because this is 2 pi over 3. This same distance would be 4 pi over 3. And that same distance again would be 6 pi over 3, which would get it up to 2 pi. So I'd have to keep doing that graph over and over again until I got up to here. And same thing if I worked backwards. I'll get it up to there. So if you had to, I would again draw it like this to begin with. And then if you really had to have it go in between there and draw it from 0 to 2 pi, what would that look like? So now I'm going to mark 2 pi here. Where is 2 pi over 3? Well, if I divide this into 3 sections, does that make sense that that's where 2 pi over 3 would be? And then this graph that I graphed there is split into 4 little sections. This is where negative 2 pi over 3 would be. And then I still didn't give myself quite enough room. We'll just pretend it's to scale. And negative 2 pi is there. So what we graphed, we had our sinusoidal axis at 2. We marked our maximum at 2.25 and 1.75. We shifted it over, and we ended up getting this is our graph between 0 and 2 pi. You would have to have another one of these between this one and another one of these right to 2 pi. That would graph it all the way up to 2 pi. It would have 3 little periods in there because every 2 pi over 3 it repeats itself. And the same thing as you're working backwards. There's one, there'd be another one, there would be another one. More or less. Yes? For the test, what I'll get you to do is usually on the test or the exam, they'll say graph at least one period of. So then you can just do this, which is much nicer. And the idea is if you needed to, you could extend it, and if you had nice graph paper, it would be easy to do that. But by doing one period, you're showing, I know what it looks like, and I could extend it further if needed. It just gets a little bit congested when you do that. The reason they're wanting you to do that is because if we looked at what does a regular coast graph look like, our regular coast graph starts here and ends there. Can you see that your graph has been squished horizontally? Can you see that it's been squished vertically? Comparatively to what our original coast graph looked like, yes, it has changed a fair bit. Questions you can do for this one are 3, 8, 9, 10, and 11. Put a little star beside 11 because in 11 it has a horizontal stretch and a horizontal translation, but it's not factored out. Do you see how this one was already factored out? That 3 was factored out, but in question 11 it's not factored out. So just a reminder of that idea from our transformations unit that we always have to remember to factor something out.